Hello, welcome back to the playlist of topics on regression models and statistical machine learning. I am Hemakumar Kasala, and as part of this video, we learn in detail the second method, namely the best subsets method in building the multiple linear regression models. In this part of the video, we learn about selecting the final model among a set of best models. We learn the application of the objectives criterion to analyze the performance of each of the models from the subset of the models. We take a deeper insight into the additional statistical outputs to choose the final model among the competing models. And finally, we analyze the residuals in order to conclude if transformations are needed on certain variables and if interaction terms are to be included to further enhance the model performance. Let's get into the video. Lecture 11. Multiple linear regression model building best subsets method. The basic idea of the best subsets regression method lies in identifying a subset of candidate predictors that together constitute a model which meets a predefined set of objectives criteria, like the ones among higher values of R square, adjusted R square, and predicted R square, and lower values of mean SSR, mallow CP, and or information criteria statistics like AIC, BIC, and APC. Which ones among the above list of statistics are emphasized as criteria depends on the problem at hand. The decide model is chosen by carefully evaluating the criteria among the competing models, and if needed, additional steps, which we will discuss soon, are taken to arrive at the final model. Let's now get into the detailed steps involved in carrying out the best subsets method. Step 1. The very first step is to identify all the candidate predictors. Make sure that you do not leave out any potential candidate predictor or predictors out of the list. If we miss out on the candidate predictors that influence the outcome, then we will finalize a model that is for sure an underspecified one. Matrix plot between the response variable and each independent predictor variable is one way to identify the potential candidate predictors. Linear relationships, weak or strong, is easily observed in the matrix plots. Nonlinear relationships, if any, are also identifiable. Step 2. Build models with all possible combinations of candidate predictors. That is, each model comprising a unique combination of candidate predictors. For example, if there are n candidate predictors, build the following sets of unique models. One model with no predictor included, n models with one unique predictor in each, n factorial divided by 2 factorial multiplied by n minus 2 factorial models with unique pairs of predictors in each, n factorial divided by 3 factorial multiplied by n minus 3 factorial models with unique combinations of 3 predictors in each, and so on, and one model with all n predictors included. Step 3. With n candidate predictors, we land in building a total of 2 power n candidate models. That can be a huge number of models to handle if n is big. One way to restrict this high number of candidate models is to pick either one or two models only from each group, where a group means the set of models with fixed number of predictors. For example, like in one model with no predictor, two best models with one predictor in each, two best models with two predictors in each, and so on, and two best models with n minus 1 predictors in each, and finally one model with n predictors. We use the term two best models for each group repeatedly above. What does a best model mean? How do we qualify a model as a best one? Typically, the models that deliver higher values of R square and adjusted R square and lower values of mean residual sum of square MSR qualify through this initial filtering as best models. Arriving first at 2 raised to the power n candidate models and choosing two best models from each group can be cumbersome if n is large. but the statistical software packages available can do this job for us. Step 4 is the final step wherein the final model that comes closest to meet the objectives criteria is chosen from the list of models shortlisted across groups in the previous step. This is an elaborate step wherein residual analysis are carried out between the contesting models, transformations are applied where nonlinearity are observed, and interaction terms are added where necessary. These steps are carried out until a final satisfactory model is arrived that satisfies the objectives criteria, represent the population data faithfully, and importantly, answer the primary research question that motivated this regression exercise. Let's understand through examples how the objectives criteria help reduce a large number of candidate models to a handful of models for detailed analysis. Let's revisit the cement data, where the research question is to understand how the composition in cement affect the heat generated in calories per gram during the hardening process. Here is the data from 13 different batches of cement. As discussed in the previous lecture, response Y is the heat generated in calories during the hardening of the cement on a per gram basis, and the 4 candidate predictor variables that constitute the composition of the cement. Running the best subsets method on this data, Minitab provides the following table as one of its outputs. We discussed the structure of this table in our previous lecture on malloc. Hence, please revisit and recap on the same in case you do not recall completely. Let's look into how we look at each of the statistics to evaluate the objectives criteria to further reduce the list of candidate models before finalizing the best model. Let's start with R square. R square increases with the number of predictors included in the model, and it is maximum when all predictors are included. Does it mean the R square is not useful in evaluating the criteria? The answer is no. By observing the increase in R square for every single predictor included in the model, we can judge the relevance of that particular predictor added to the model. We find the biggest jump in R square between the 1 predictor model in row 2 and 2 predictors model in row 3. The increase in R square value with subsequent inclusions of 1 predictor at a time is quite small compared to the above and not significant. Therefore, based on the increment in R square value criteria, the model in row 3 with x1 and x2 predictors included seems to be the best model. Let's move on to the next possible objective criteria, the adjusted R square. Please recall adjusted R square equals 1 minus n minus 1 divided by n minus p multiplied by regression sum of squares SSR divided by total sum of squares SST, where p equals vars plus 1. With a small rearrangement in the denominator, we get adjusted R square equals 1 minus n minus 1 divided by SST multiplied by SSR divided by n minus p. Since SSR divided by n minus p equals mean residual sum of squares MSR, adjusted R square equals 1 minus n minus 1 divided by SST multiplied by MSR. The mean residual sum of squares MSR is the average or mean value by which a predicted response deviates from its respective actual value. We would always prefer a low mean residual sum of squares MSR. Lower value of MSR results in higher value of adjusted R square and vice versa, since adjusted R square equals 1 minus n minus 1 divided by SST multiplied by MSR. We can observe the relationship between the adjusted R square and MSR in the table below. S in the table is nothing but MSR. Low adjusted R square and we see a high MSR value. High adjusted R square and we see lower MSR value. Therefore, going by the criteria higher adjusted R-square and lower MSR, we land up in choosing the model in row 5 with x1, x2 and x4 as predictors as the best model. Criteria R-square recommends the model in row 3 with two predictors x1 and x2, and criteria adjusted R-square and lower MSR recommends a model in row 5 with three predictors x1, x2 and x4. Note, the model in row 3 with two predictors x1 and x2 is simpler compared to the three predictor model in row 5. However, predicted R-square value in the three predictor model in row 5 is little better than the two predictor model. The difference though is quite small that the predicted R-square need not be the deciding criteria in this case. Let's turn our focus on the last statistic in the table, malus-CP, as an objective criteria. Recall that the malus-CP criteria suggests that the model whose malus-CP is less than or equal to P, which is VARS, where VARS is the number of predictors included in the model, plus 1, is the one with the least bias. As per this criterion, three models meet the requirements, where malus-CP is less than or equal to VARS plus 1. While the models in row 3 and row 5 have already qualified for the best model contest based on the previous two criteria, malus-CP suggests one more model in row number 6. Model building does not stop with evaluating just the objectives criteria. A lot more statistical results require attention too. For further exploration, let's start with the model in row 5 with three predictors x1, x2 and x4. Analysis of variance table for the model with three predictors x1, x2 and x4 as provided by Minitab is as follows. Everything looks okay but for p-value for the f statistic associated with predictor x4. At 0.205, the p-value is definitely on the higher side. The typical value is 0.05. Coefficients table for this model as provided by Minitab is as follows. We encounter a new statistic, namely VIF, which is variable inflation factor. We will understand the statistic in detail later, but for now, VIF indicates if there exists any strong correlation between any two predictors included in the model. Note, we are talking about the correlation between the predictor variables and not between the response and a predictor variable. High values of VIF suggest a strong correlation between x2 and x4. The matrix plot indeed shows this strong negative correlation between x2 and x4. The correlation coefficient R in this case is minus 0.973. We get to see relatively high values of standard deviation against the estimated values of the respective slope coefficients. Large variance in x2 and x4's estimated slope coefficients is an indication of presence of multicollinearity, as it is called, between x2 and x4, resulting in high values of VIF between them. We will discuss on multicollinearity in detail later. High values of VIF is as such not a problem as long as the objective of this exercise is to describe the overall variation in the response variable using the constituent predictor variables. The estimated regression function in this case is given by y hat equals 71.6 plus 1.452 multiplied by x1 plus 0.416 multiplied by x2 minus 0.237 multiplied by x4. The problem arises only when the objectives of the model also aims to measure the influence of each of the predictor variables that exhibit multicollinearity on the response variable. Such measurements shall often be incorrect. To state 0.416 is the change in the estimated response y hat for one unit change in x2, when there is no change in x1 or x4, and minus 0.237 is the change in the estimated response y hat for 1 unit change in x4 when there is no change in x1 or x2, shall often be incorrect. Now let's take a look at the statistical parameters that the model in row 6 with 3 predictors x1, x2 and x3 offers. This was one among the 3 models that Mallow-CP criteria suggested. Analysis of variance table for the model with 3 predictors x1, x2 and x3 as provided by Minitab is as follows. Like in the previous case, the p-value for the f-statistic associated with predictor x3 is on the higher side. It's greater than 0.05. Coefficients table for the model as provided by Minitab is as follows. Let's take a look at the VIF values. We do not see very high values for VIF. Therefore, multicollinearity is not a concern in this model. The matrix plot shows perhaps a faint negative correlation between x1 and x3, though not as strong as one between x2 and x4. We see relatively a high value of standard deviation in case of x3's estimated slope coefficient. Little higher value of VIF, though not significant for x3 as well, possibly because of the faint negative correlation with x1. Therefore, no multicollinearity in comparison with the model in row number 5 with predictors x1, x2 and x4, and the statistics used in objectives criterion are almost the same as that of the model with predictors x1, x2 and x4. Finally, how does the model in row number 3 with 2 predictors x1 and x2 compare against the 3 predictor ones? Let's check how does this model fare in terms of the other additional statistics. Analysis of variance table for the model with 2 predictors x1 and x2 as provided by Minitab is as follows. P-values are almost 0 with healthy f-statistic values. That's what we see. Coefficients table for this model as provided by Minitab is as follows. We see very low values for VIF and therefore no multicollinearity whatsoever. The variance in the estimated slope coefficients for x1 and x2 are low and look more than acceptable. T-statistic and corresponding p-values also look very convincing. And we already know the statistics used to evaluate the objectives criterion look convincing as well. With all the statistical parameters healthy and considering simplicity with just 2 predictors, doesn't the 2 predictors model with x1 and x2 fare much better than the 3 predictors ones? Unless there are other compelling scientific or technical reasons, the 2 predictors model with x1 and x2 indeed fare better among the competing models. Please recall, even the stepwise model building method that we discussed previously converged on the same 2 predictors model with x1 and x2 as predictors. Is that all? Can we conclude on the 2 predictors model with x1 and x2? Not yet. We still need to do residual analysis and check if transformations on predictors or the response variables, if any, are required. Is there any need to introduce interaction variables to arrive at still better results? Residuals are plotted against their respective fitted values. That is, residual at each predicted value is plotted against that predicted value. Residuals are seen spread across 0 uniformly. No specific pattern is seen, suggesting no nonlinearity. Constant variance is observed, in other words, no increasing or decreasing variance, for example, which suggests the fit is good, confirming a linear relationship between the predictors and the response. With residuals spread evenly across 0, The next check is to verify if the error or residuals conform to a normal distribution. The normal probability plot is drawn to check the normality in error distribution. Normal probability plot indeed shows more or less a linear graph confirming a fairly good normal distribution of the error or the residuals. Therefore, the simpler model with two predictors x1 and x2 passes through all statistical evaluations and appear the best among the competing models. The estimated regression equation for the best model chosen is therefore y hat equals 52.58 plus 1.468 multiplied by x1 plus 0.6623 multiplied by x2. That brings us to the end of the lecture on model building using best subsets method and other statistical evaluations. See you back soon with the next lectures on this topic on multiple linear regression models. Bye for now.